Hello, Chem 1A. This is Chapter 8, Lecture Video 3, and we're going to be discussing Bohr's model of the atom. Niels Bohr was pretty much a famous physicist slash chemist, and he came up with a model for the atom that was different than previous predictions, right? The model before him was the Rutherford model, which stated that electrons just kind of freely circled the atom's nucleus, kind of could be anywhere they want at any distance they want. Niels Bohr said that electrons orbit the nucleus like planets around the sun. And what he means by that is we have our sun, right? Big yellow ball of energy. And we have our planets orbiting at very discrete, I mean, they should be ellipticals, but you get the idea, discrete distances from the sun. And so the nucleus in our atom is the sun, and our electrons can actually only orbit at specific rings around the sun now, or the nucleus in this case. He theorized that these orbits therefore are quantized. Now, what does that word quantized mean? So we're going to talk about two systems here, a quantized system and what we call the opposite of a quantized system, a continuous system. Now, I like to use staircases versus ramps as an example of this. In a quantized system, let's say we're a person and this is a really tall staircase step. It's like half our body up, but we're going to pretend this is a taller stick figure. And where can we put our feet on this staircase, right? I could put my foot here. I could put my foot here. I could put my foot here or there. At any step on the staircase, I can put my foot. But if I try to put my foot halfway up a step, I'm probably going to fall, right? You can't actually put your feet halfway up the step. This is what we call more of a quantized system, where there are only specific possible answers allowed, right? You could be there at, let's say if this is step 1, step 2, step 3, step 4. You could be at step 1, you could be at step 2, you could be at step 3, you could be at step 4. Step 3.5 is impossible. There's no such step. You can't be there. It's not possible to have that numeric value associated with your orbital, or in this case, orbital, right? But in this case, step. And that's what a quantized system is. It's a system where only very specific numbers are possible. In the opposite scenario, we have what's known as the continuous system. And I like to think of a ramp as a continuous system. Now, in the continuous system, I can put my feet anywhere I want on this ramp, and I'm going to be fine. I'm not going to fall down. This is more like what we call a continuous system, where there's a gradient from one number to the next. Any value between two numbers is technically possible. And these are the major distinction between a quantized system and a continuous system. Now, quantized systems tend to be a little bit more hard to understand theoretically or to really just conceptualize, because most systems that we're familiar with are continuous. The clock, the second hand, slowly moves from one number to the next, moving between an infinite possibility of numbers as it goes from like 1 second to 2 seconds, right? That's a continuous system. But atoms, electrons around the nucleus of our atom, they orbit in this quantized system where there are only specific possible locations they can hang out. So to continue talking about what Niels Bohr then predicted was, he said, like I just mentioned, that we have these orbitals that are only possible location for electrons to hang out are in these rings around the nucleus. The nucleus in this example being my plus sign, because nuclei have positive charges. So an electron can exist right on this ring, orbiting at that distance, or it could orbit at a different distance, right? It could orbit here, or it could orbit all the way out here, or it could orbit here at these different distances from the nucleus. These different distances he called energy levels or energy level states. And so what he said was the closest ring is energy level 1, and the second closest was energy level 2, and he just counted using whole number values out from the nucleus. These energy levels can go up to almost infinity pretty much. n is equal to 1, or the lowest energy level that our electrons can hang out at, is what we call the ground state. And this is all for hydrogen. Hydrogen only has one electron, so I have all these green dots here. Really, the electron could be at energy level 1. In this scenario, in a hydrogen atom, since hydrogen only has one electron, that electron we'd say is in the ground state. However, if I had that electron in any of the other orbitals, let's say here, right, on energy level 3, use the same color, that would be what we call an excited state. And so any of the other energy levels in the hydrogen atom for its one electron hanging out at anything other than 1 is going to be an excited state. For other elements where they have multiple electrons, that might not be true. It might be still in the ground state even if we're not in energy level 1. So one of the biggest deals is that electrons, they can move between energy levels. Let's say I have my electron sitting pretty up here in energy level 4. Well, it can drop down back to energy level 1, and when it does that, it releases energy. And typically that energy is released. That's a really bad wave, but it's a photon of light in a wave, right? And we can see that energy being released. So one of the things that we do need to talk about are what are known as atomic orbitals. Now, energy levels, the Niels Bohr things that we just talked about, are in fact very different from what we call atomic orbitals these days. Atomic orbitals are kind of the shapes that electrons actually are present around the nucleus in. Now, one of the major misconceptions about our orbitals, quote unquote, is that our electron is actually orbiting in the shape that the orbital is in, right? Our electron does some weird thing here where it wraps around or whatever. These shapes are not the path the electron is taking around the nucleus. They're what we call probability boundaries. Now, what that means is that inside these shapes, there is a high probability of finding an electron. What we're going to learn later in this chapter is that we can't know both the energy and position of an electron at the same time in great levels of accuracy. As we know more about one, we know less about the other, which is known as the uncertainty principle, Heisenberg's uncertainty principle. What that means is I can never actually know exactly where an electron is in an atom. Part of this is due to the fact that they're moving at very near the speed of light, and as soon as I know where it is, it's not there anymore. It's moved somewhere else in the atom. But anyways, these shapes are within the shape. There is usually a high probability of finding an electron, usually upwards of like 99% probability of finding an electron. Outside of the shape, there is a 0% probability of finding the electron. So molecules and atoms can absorb energy and emit energy, right? They do this by moving between energy levels, right? Our electrons can move from a lower energy level to a higher energy level. They can do that by absorbing energy. So for instance, in the last 2 slides back, I mentioned that an electron in hydrogen's energy level 4 could drop down to energy level 1. If it did that, it's going to be releasing energy because it was at a higher energy state, went down to a lower one. It's going to release that energy as light. But because our orbitals or our energy levels are quantized, only very specific amounts of energy can be absorbed or emitted. Max Planck, same guy that came up with our E is equal to Planck's constant times frequency, proposed that these energies are quantized, meaning that only certain wavelengths of light or electromagnetic radiation can be emitted or absorbed by these atoms, and this backed up Niels Bohr's original model of the atom. So if we look at the energy levels in an atom, here is a general picture of what you're going to see. Now, this is a really great picture. Now, we'll get to the equation in just a second. As you go up in energy, so in this picture, energy is increasing as we go from the bottom of the picture to the top. You can see initially we're at energy level 1, which is our ground state. It's our lowest energy level state that we can be at. And one of the biggest things that you need to know and need to understand about this kind of picture, and you should be able to picture these energy levels in your head, is there is a huge energy difference between energy level 1 and 2. And as we go up in higher energy levels, the energy is higher, but the distance between, or the difference between in energy between one energy level and the next starts to shrink as we go higher and higher in these energy levels. And that's something you should know. Now, how do we calculate the energy that an electron needs to be at in order to be at one of these energy levels? Well, that's using this equation right here. Now, R, H, and C are all constants. And Rydberg's constants, the R, H is Planck's constant, C is speed of light, and they're all constants. They're all going to be provided, or they'll be calculated for you in the equation. This equation is not actually one we use very often, and I don't really expect you to use it on the test or know it even. We're going to use a different equation later in the chapter, on the next lecture video actually, that is way more useful, and that one will be given in the equation bank. So cool. Electrons can move up in energy from one energy level to another. They can do this by absorbing energy, either from heat, electrical, or even light. If they drop back down, though, let's say they're at energy level 6 and they drop down to energy level 1, they're typically going to release that energy as a photon of light, right? And we can see that light and measure it. All right, if you have any questions, as always, please feel free to contact me via office hours or email, and we can set up a time to meet.